Welcome to the Explainer. Today, we're diving into something pretty incredible, a real high-wire act of modern medicine, intravenous anesthesia. We're going to look at the amazing science that goes into getting that dose just right.
So how do you hit a moving target you can't even see? Well, that's exactly the challenge an anesthesiologist faces every single day. They have to deliver these super powerful drugs to a patient's brain, a target they can't physically see, right? All to achieve this very precise, very safe level of unconsciousness.
And you've got to understand, this is a constant, delicate balancing act. I mean, think about it. If you give too little, you risk the absolute horror of a patient waking up during surgery. But if you give too much, well, you're looking at dangerous side effects. It's this continuous tightrope walk between being effective and being safe. So, to really get how they pull this off, here's what we're going to cover. We'll look at the core challenge, follow the drug's journey, understand its power, see how the perfect dose is made, and then check out the amazing tech that brings it all together. All right, let's get into it. Section 1, the anesthesist's core challenge. You know, this whole idea of controlling consciousness isn't new at all, but being able to do it with the kind of precision we see today, that's a very recent thing, and it's built on centuries of discoveries. It really all started with just figuring out the basics. Like, back in 1628, William Harvey figured out that blood actually circulates. And get this, not long after, Christopher Wren was already experimenting, injecting drugs into dogs using a feather quill. Fast forward to the 1930s, and IV induction finally becomes common. But the real game changer, that showed up in 1977 with propofol. This was the first drug that could both put a patient under and keep them there safely. Okay, on to the first big piece of this puzzle. It's called pharmacokinetics, or PK for short. And it's all about what the body does to the drug. It's like charting the drug's entire journey from the second it's injected. To put it simply, think of PK as the roadmap for the drug's trip through your body. It tells us exactly how the body absorbs it, distributes it to different places, breaks it down, and then, finally, gets rid of it. Now, to predict what a drug is going to do, you have to get one thing straight. The body isn't just one big bathtub where everything mixes evenly. No, it's way more complex. First, the drug hits what we call the central compartment. That's basically the blood. From there, it moves super fast to muscles and organs. And finally, it slowly seeps into tissues like fat. Understanding this flow is absolutely key to predicting how the drug's concentration changes minute by minute. Okay, so that's the drug's journey. But what does it actually do when it gets to where it's going? This brings us to the second big piece of the puzzle, pharmacodynamics, or PD. And it's the perfect flip side. If PK is what the body does to the drug, PD is what the drug does to the body. And this is so important. The drug's real effect doesn't happen in the blood. It happens at its final destination, which, for these drugs, is the brain. So that means when we measure the drug concentration in a blood sample, it's really just an estimate, a proxy, for the concentration that's actually doing the work and putting the patient to sleep. Which, leads to a really interesting question. If the drug is in the bloodstream pretty much instantly, why isn't the effect instantaneous? Why does it still take a minute or two for the patient to drift off? The answer has this fancy name, hysteresis, but all it really means is that there is a delay. It's the time it takes for the drug to make that final leap, to travel from the blood, get across the blood-brain barrier, and actually start doing its job on the brain's receptors. And as you can see here, that delay is totally different for every drug. Take a look at alfentanil. It hits its peak effect in just over a minute. That makes it perfect for something really fast, like intubation. But then you have fentanyl, which takes more than 3.5 minutes to peak. It's absolutely crucial for clinicians to know these times inside and out, so they can line up the drug's peak power with the most intense parts of the surgery. And of course, it gets even more complicated because these drugs are almost never used by themselves. The key concept here is synergy. It's like a 1 + 1 = 3 situation. You take a hypnotic like propofol, that's for sleep, and you combine it with an opioid like fentanyl, that's for pain. They actually amplify each other's effects. This is the whole idea behind modern balanced anesthesia, and it means you can use smaller and therefore safer doses of both drugs. Okay, so we've got the science down, PK and PD. But how do you take all that theory and use it to craft the perfect dose for a real person right there in the operating room? Well, you've kind of got two bad options if you keep it simple. You could give one big shot, a bolus, which works fast but gives you this risky initial spike and then fades unpredictably. Or you could do a slow, continuous IV drip. That's safer, but way too slow to be practical. So what's the solution? You combine them. You start with a smart bolus to get the patient to the right level fast, and then you follow it with a constantly adjusting infusion to keep them right in that sweet spot. But look, getting the patient to sleep is really only half the battle, right? The other, and I'd say equally important challenge, is making sure they wake up on time and predictably when it's all over. Now you might think, oh, it's just the drug's half-life, right? The time it takes for half of it to leave the body. But when you're talking about infusions, that's actually super misleading. What really matters is the context, and by that, we mean how long the infusion has been running. And this chart right here shows you exactly why that context is so critical. Look at fentanyl. The longer the surgery goes on, the more it builds up in the body's fat stores, and the longer it takes for the patient to wake up. But then, check out remifentanil. Its wake-up time is short and super predictable, whether the surgery was 1 hour or 8 hours. This was a revolutionary change in how we control anesthesia. So, trying to manage all these variables in your head, PK, PD, context-sensitive half times, it's basically impossible for a human to do perfectly, and that's where technology steps in. Let me introduce you to the smart pump. This amazing tech is called Target Controlled Infusion, or TCI. Here's how it works. The clinician just plugs in the patient's info, like age, weight, and so on, and then they just set a target for the drug concentration. That's it. From there, the pump's built-in computer, which is loaded with all those complex mathematical models we've been talking about, does all the heavy lifting. It calculates the exact infusion rates needed to hit and maintain that target all in real time. And these pumps just keep getting smarter. The first versions were designed to target the drug concentration in the plasma, in the blood. But the real cutting-edge stuff today is effect site targeting. These pumps use even more advanced models to predict and control the drug concentration right where it actually matters, in the brain itself. And that means even faster and more precise control than ever before. But believe it or not, even the incredible TCI pump isn't the end of the story. The future of anesthesia is heading somewhere even more amazing, towards totally personalized and automated dosing. So what does that look like? Well, the next big thing is true personalization. We're starting to see universal models that can work for literally any patient, from a small child to an elderly adult. But the ultimate goal, the holy grail, is a fully closed-loop system. Imagine this. A brain monitor, like an EEG, is constantly reading the patient's brainwaves, feeding that data directly to the pump, and an AI is adjusting the dose second by second, automatically. A completely automated and responsive system. And all of this brings us to one last, really provocative thought. As these systems get smarter and more automated, what happens to the role of the human expert? Is the anesthetist of the future still a hands-on clinician, or are they more of a systems manager, overseeing the tech, or maybe something new entirely, a partner working alongside an incredibly sophisticated algorithm?